There is a component inside your smartphone designed to solve a problem from the 1950s by a small group of radio hobbyists who never imagined a phone. They were trying to fit a single human voice into half the radio space it normally took up. So they refined a filter sharp enough to slice one clean voice out of a band full of noise. That same filter now sits inside a modern smartphone, copied and shrunk dozens of times over. This is the story of how it got from a ham radio workbench into your pocket. Start with the problem the hobbyists were actually facing. On the shortwave bands, an ordinary voice transmission, the kind used in early AM radio, actually sends the same information twice. The microphone's signal gets stamped onto a carrier wave, and that produces two mirror image copies of the voice, one just above the carrier frequency and one just below, each holding identical audio. Engineers call those the two sidebands. Sending both of them, along with the carrier itself, eats up roughly twice the bandwidth the message really needs. And on a band already packed with stations, that waste was expensive. For amateurs squeezed into narrow slices of shortwave spectrum, having the space a conversation took was not a luxury. It was the difference between getting through and being buried under the neighbors. The fix, a technique called single-sideband, was to strip away the carrier and one of the two mirrored copies and transmit only the sideband that remained, so the same conversation fit in half the space, with far more of the transmitter's power going into the part that actually carries the voice. But there was a catch, and it was a hard one. To keep just one sideband, you need a filter that passes the frequencies you want and violently rejects the ones sitting right beside them. For speech, the lowest audio tone is usually treated as around 300 Hz, which means the wanted and unwanted sidebands are separated by a gap of only about 600 Hz. To knock the unwanted side down by 40 decibels or more across that sliver of frequency, the filter's response has to be almost a vertical wall, what engineers call sharp skirts. Ordinary circuits built from coils and capacitors cannot cut anywhere near that steeply. You need resonators with an extraordinarily high-quality factor. And in the 1950s, that meant one of two things: quartz crystals or precisely machined metal. That high-quality factor traces back to a discovery made decades earlier in a Paris laboratory in 1880. Two brothers, Pierre and Jacques Curie, showed that certain crystals, quartz among them, produce a small electric charge when you squeeze them and flex slightly when you apply a voltage. That two-way relationship between an electrical signal and mechanical motion is called piezoelectricity, and it turns out to be the quiet thread running through this entire story. A slab of quartz cut the right way doesn't just conduct a signal, it vibrates at an incredibly stable, sharply defined frequency, like a tuning fork made of stone. That stability is the whole point, because the cleaner a resonator holds its frequency, the steeper the filter you can build around it, which is exactly the near vertical wall that single sideband demanded. By 1929, an engineer at Bell Laboratories named Warren Mason had worked out how to build those quartz crystals into filter networks. The telephone company used them to stack 12 separate voice conversations onto a single pair of copper wires, each call in its own narrow slice of frequency, kept apart by crystal filters sharp enough that the conversations never bled into one another. So the core idea, using a vibrating piezoelectric crystal as an almost perfect frequency gatekeeper, was already proven inside the telephone network before the radio amateurs ever picked it up. What the amateurs did was aim that same idea at a different target and turn it into something you could build in a garage. By the late 1940s, single sideband was moving out of the telephone labs and onto the amateur bands. Oswald Villard, an electrical engineering faculty member at Stanford, put the university's radio station on the air with a single-sideband voice transmitter, and in 1948 the amateur radio magazine QST began running a monthly column devoted entirely to the technique, and it spread fast through the hobbyist community. In 1951, two contributors named Weaver and Brown published detailed crystal lattice filter designs in QST, showing amateurs how to select one sideband and reject the other using banks of quartz crystals wired onto a homemade metal chassis. But the crystal approach had a rival. A few years earlier, in 1946, an engineer at Zenith named Robert Adler had built a filter that worked mechanically instead. Inside a metal tube barely larger than a cigarette, a row of precisely ground metal discs was coupled together so the assembly resonated at 455 kilohertz, filtering the signal through physical vibration rather than a crystal. Collins Radio, a company in Cedar Rapids, Iowa, founded by the lifelong amateur Arthur Collins, took that mechanical filter into volume production in the early 1950s. Its receiver, the Collins 75A4, released in 1955, is widely regarded as the first production single-sideband amateur receiver using a plug-in mechanical filter to shape its passband. Paired with its matching transmitter, the set cost around $2,500, so much for the era that hams nicknamed the pair the Gold Dust Twins, and it stayed out of reach for most hobbyists. But the design worked, and within a few years, the same filtering trick the amateurs had refined was flying on American bombers, after Collins gear was demonstrated aboard a Strategic Air Command aircraft in 1956 and single sideband became standard for long-range military communication. For about a decade, the sharpest filters in radio stayed physical objects you could hold in your hand, quartz crystals and machined metal discs. That changed in 1965 when two researchers, Robert White and Fred Voltmer, introduced a device called the interdigital transducer that sidestepped the solid crystal altogether. Instead of sending vibrations through the bulk of a crystal, they laid a set of interlocking metal electrodes, shaped like the fingers of two combs pushed together, onto the polished surface of a piezoelectric wafer. A signal applied to those electrodes launched a tiny acoustic wave that rippled across the surface, and the spacing of the fingers decided exactly which frequencies survived the trip. This was the surface acoustic wave filter, and it could be manufactured photographically, printed onto a substrate, much like a modern circuit is printed onto a chip. That manufacturing shift mattered as much as the physics did, because a filter you can print by the thousand is cheap, and cheap is what eventually let it slip into a mass-market consumer device. The technology grew up first inside radar systems, then moved into television sets, where it replaced bulky, tuned circuits in the picture and sound stages. And here the story loops back on itself, because Robert Adler, the same Zenith engineer who had built that mechanical disc filter in 1946, was also an early pioneer of surface acoustic waves in television. One man's career physically connects the machined metal era to the printed chip era. By 1975, the Japanese component maker Murata had surface acoustic wave filters in mass production, and over the following 2 decades they worked their way into cordless phones, pagers, and eventually the first cellular handsets. The surface acoustic wave filter had a ceiling, though. It worked beautifully at the frequencies used by early mobile phones, but as the industry climbed toward higher bands, the surface wave started to run out of room. The answer was to send the acoustic wave back down into the material, but this time through an ultra-thin film rather than a bulky crystal. In 1993, the research labs at Hewlett-Packard began developing what became the thin-film bulk acoustic resonator, usually shortened to FBAR. The team stacked a film of piezoelectric material, typically aluminum nitride, only a few thousandths of a millimeter thick, between two electrodes, so the sound wave bounced vertically through the film at frequencies far above anything a surface device could reach. In 2001, after the group had passed to Agilent Technologies, they shipped the first commercial bulk acoustic wave duplexers for mobile phones, prized because they were dramatically smaller than the ceramic filters that phones used at the time. They also held up to more transmit power without distorting, which mattered as phones started pushing their signals harder to reach distant towers. The technology then scaled at a pace that is hard to picture, because by the middle of 2008, more than 1 billion of these bulk acoustic wave filters had been sold. It was the same piezoelectric effect the Curie brothers had demonstrated on a Paris workbench, and the same sharp-skirted filtering the ham operators had needed, now shrunk down to something you would need a microscope to inspect. All of this raises an obvious question. Why would a single phone ever need dozens of these filters? The answer is that a modern smartphone is not one radio, it is a dense cluster of them running at the same time. It handles second, third, fourth, and fifth generation cellular signals across dozens of separate frequency bands, plus Wi-Fi, Bluetooth, GPS, and the near-field chip that lets you tap to pay, all packed into a sealed case a few millimeters thick. Every one of those transmit and receive paths needs its own filter to pass its assigned band and reject everything else, or the radios inside the phone would drown one another out. Picture a Wi-Fi radio and a nearby cellular band, both active a few millimeters apart inside the same case, each one strong enough to swamp the other. And the only thing keeping them politely separated is a filter tuned tightly enough to admit one and shut the other out. Engineers call this the coexistence problem, and it has gotten harder with every generation of the network. A first-generation phone from the 1980s needed only 1 or 2 crude filters and could not even send a text message. Fourth-generation handsets built for worldwide roaming carried somewhere between 50 and 90 of them. Premium fifth-generation phones pushed that count toward 100. Part of the reason is that the core fifth-generation bands are enormously wide, demanding several hundred megahertz of bandwidth, where a typical fourth-generation band needed only around 60, which is exactly the kind of job that favors bulk acoustic wave filters over the older surface type. In late 2025, the filter maker Qorvo put it plainly, stating that today's premium smartphones contain nearly 100 filters, spanning everything from low-band cellular up to Wi-Fi. That demand has turned the humble filter into one of the most valuable and fought-over pieces of the entire wireless industry. The research firm Yole Group valued the mobile radio frequency front-end market, the bundle of chips that includes these filters, at $15.4 billion in 2024, sitting inside a total radio frequency market worth $51.3 billion. The companies that make them have been consolidating hard. Qualcomm bought out its filter joint venture with the Japanese firm TDK in 2019 for over $1 billion. Broadcom still carries the original FBAR lineage, the direct corporate descendant of that Hewlett-Packard project from 1993, and supplies filters for Apple. And in late 2025, the 2 largest American suppliers, Skyworks and Qorvo, announced they would merge in a deal valued at roughly $22 billion, a measure of just how much money now rides on components almost no one will ever see or name. Which brings the story back to where it began. The next time you make a call, or your phone quietly passes your data from one cell tower to the next without dropping the connection, it is worth remembering what is doing that work. Somewhere in that sealed glass case, a row of tiny piezoelectric resonators is performing almost exactly the task a slab of quartz performed on a hobbyist's workbench in 1955, passing the signal you want and rejecting the noise you do not. The people who refined that filter were only trying to fit one clear human voice into a crowded band of shortwave static. They had no way of knowing they were also building a small, essential piece of the device that would end up in nearly every pocket on Earth.